Hello everybody, it's Mr. Slamka, and I wanted to talk to you about section 7.5 today, which is using properties of trapezoids and kites. Trapezoids and kites are going to be our last two quadrilaterals. Let's start with trapezoids. So a trapezoid is going to be a quadrilateral with exactly one pair of parallel sides. Now this is interesting because the way that it is being defined right here is it's kind of being defined by something that it's not. It needs to have exactly one pair of parallel sides and no more. So that means that you can only have one set. The other set must not be parallel at all, which is what I have drawn here. Now also, I've drawn this picture of this trapezoid, and it is a trapezoid, but I've drawn it specifically because I'm going to guess that this is not a trapezoid that you have in your mind. Most of the time, these sides that are parallel are known as bases, and so bases are usually at the bottom, but I've drawn them on the sides because they can be on the sides. Now the one right below this is probably more of what you think about when you think about the word trapezoid, and that is an isosceles trapezoid. So right off the bat, it does have its base at the bottom and then another one at the top, so that is a little bit nicer. And the other thing that it has is it has a set of congruent sides over here and over here. The sides that are not parallel are congruent. So that guy right there is an isosceles trapezoid. It's an extra special one. And because it is so special, we'll spend quite a bit of time talking about it today. Now, our other shape that we have for today is a kite. Now, a kite is going to once again be defined a little bit more strictly. You need to have two sets of congruent sides, but the thing is that the congruent sides are going to be consecutive and not opposites. So opposite sides are not congruent. So that means that if we reach from one side of the kite over to on the opposite side over here, they will not be congruent at all. So this is once again kind of being defined by something that it is not. Okay, so now once you have those basic shapes, here are a couple of theorems that you can use that are going to kind of bump them up. Now right off the bat, if you hadn't noticed already, most of these are about the isosceles trapezoid because that's a little bit more strict and there's a little bit more to go off of there. So an isosceles base angles theorem, it says that if a trapezoid is an isosceles trapezoid, then each set of base angles is going to be congruent. Now once again, people think about the bases being down here at the bottom, which is true, but there's also a set of bases that are going to be base angles that are up at the top as well, so don't forget about those. Now this exact same theorem works backwards as well, so that means that if you start off with the base angles, you can end with the fact that you are isosceles. So the way that that is really working between these two theorems is the way that a converse always works. For the regular base angles theorem, you're starting with isosceles and you're ending with base angles. For the converse, you're starting with the base angles and you're going to isosceles. So it's a little bit backwards, and that's good. Next, the diagonals theorem. The diagonals theorem for an isosceles trapezoid states that the diagonals will be congruent. So now this is a little bit hard to signify, but that diagonal right there is going to match the same length as this diagonal right here. That's not true for all trapezoids, but it is true for the isosceles ones. Now the last one, this one's a really, really great one. This one's the trapezoid mid-segment. This is not just about isosceles, it's true for all trapezoids. And basically what we have right here is a mid-segment, which means it is a connecting segment between two midpoints, M and N. You can see that they're midpoints by these tick marks that I have on the right side and the left side. And the deal here is that you can actually determine the length of this midsegment very, very quickly and easily using a simple formula. The simple formula states that the midsegment is equal to half of the sum of the small segment, which in this case is AB, plus the large segment, which in this case is DC. Basically what this is stating, even though it doesn't really look like it, it says that the midsegment is the average. You take the one that's too small and you pair it up with the one that's too big and you get the average length right here in the middle. So that is what we've got going on right here. Kite diagonal theorem. The kite diagonal theorem right here is going to be not very surprising. If you have a couple of diagonals on your kite, what you're going to find out is that they're going to create a particular angle. If you look at the diagonals that I drew, it becomes very clear the angle that we're looking for is a perpendicular 90-degree angle. Just a quick reminder, this is the symbol for perpendicular in case you have forgotten. Last theorem that we have right here is the kite's opposite angles theorem, and the kite opposite angles theorem states that opposite angles will be congruent, but only one set. So the angle over here on the left and the one on the right, clearly not the same. They're not congruent at all. There will only be one set, and this one set is going to be the set that is between the non-congruent sides. So we've got this set of consecutive congruent sides, and this set over here, our congruent angles will be an unmatched pair. So you're going to have these two guys, one that is short, one that is long, one that is short, one that is long. Okay, so now what if I had asked you to kind of sort of prove that you have a trapezoid on your hands, or prove that you have a kite on your hands? What you would want to do is you would want to show a little bit of work like we did in section 7.3, which means I want you to use the distance formula or the slope formula to prove that you have some things that match. So in this case, what we're looking for is we're looking for a trapezoid. And so trapezoids are known for having one set of parallel sides, and parallel sides are known for having the same slope. So what I'm going to do is I'm going to calculate 4 slopes. And when I calculate those 4 slopes, I'm going to take a close look at them, and I'm going to decide if any of them match or if any of them are mismatched. So let's do it. When you're calculating these, you can calculate them the long way, which I will do a couple, and you can also calculate them on the drawing, which I will also do some. So let's do a couple of calculations for slope. All right, I'm going to start with DE. So DE is right here across the top. An easy way to get the slope for this is to look at the actual drawing. And what you can do is you can count the rise, which is 1. And you can count the run, which happens to be 3. Rise over run is 1 over 3. Now, if I also look at the drawing, I notice that CF right here looks like it would be another parallel base. So I would love to determine if that had the same slope as DE. So let's take a look at it. If we're going to go from C to F, what we could do is once again count the rise, which in this case would be 2. And then the run in this case would be a little bit longer. 1, 2, 3, 4, 5, 6. Now that fraction does reduce. 2 over 6 reduces down to 1 over 3. These two are matched. Because they are the exact same answer, that means that DE is parallel to CF. Now you might say, perfect, that's enough information to state that we have a trapezoid, but unfortunately no. Remember that a trapezoid has to have exactly one pair of parallel sides. So that means the other pair has to not be parallel. So we do still need to do 2 more calculations for slope, and we need to make sure that this is a mismatch set, not the same. And so we're going to do our same kind of calculations, except this time we're going to do DC and EF. This time I'm also going to calculate them the slow way. You don't have to calculate the slow way if you don't want to. You don't have to use the drawing if you don't want to. You can calculate slope any way you would like. You're a pro at slope. I trust your skills and abilities. I just wanted to give you some choices so you could try it out. Remember, when you are calculating the slow way, you want to do your y's on top and your x's on bottom. It is still rise over run. So when we calculate this slope, we're going to get 3 over 1. That was for DC right here. Now when I do EF, I just need something that is not 3 over 1, and that would be best. So I'm going to calculate my slope here. Once again, rise is going to be my first piece, so I'm going to calculate based off my y values. That's going to be 4 minus 2. And then I'm going to do another piece for my run, which is going to be 4 minus 6. So when I do this calculation, I'm going to end up with a 2 on top and a negative 2 on bottom, which is going to give me negative 1. Now these two do not match. They are not parallel, which is great news. We only have one set of parallel sides, which is good. So that means that we are going to wrap this up. The way that we're going to wrap this up is we're going to state that CDEF is a trapezoid, and we're going to state why we know it's a trapezoid. So we're going to state that CDEF is trapezoid. I always like to abbreviate, so I'm going to call it just a trap. So CDEF is trap, and we're going to state that it is trapezoid by, and in this case what I'm using is the definition of a trapezoid. So it's going to be CDEF is trapezoid by the definition of a trapezoid. There you go. Okay, now there is a follow-up to this problem right here, and that's part B, and it says, suppose that the coordinates of point E was at 7, 5. What would the type of quadrilateral be this time? So if we took E and we got rid of this point at 4, 4, and we bumped it up to 7, 5, if you take a look, that point E right there would now extend this line that was already going, and it would make it a little bit longer, and the line from E to F would also take a new kind of shape. Once again, slope would still be a very important thing, so we would calculate the slopes that involved E a second time. So this point E affected the slope of DE, and it also affected this line segment EF, and so we would need to recalculate those two slopes. So now DE, the new slope for DE, would still be 1/3, which would mean that that would still match with the slope of CF, which would mean that CF and DE would still be parallel. So that would mean that we would still maybe have a trapezoid, right? Well, let's take a look at EF. If we bump over to EF, we'll notice that that one has a slope of 3/1 now, which matches the slope for DC. And that would mean that DC would also be parallel to EF. And now we don't have a trapezoid anymore. Now, because we have two sets of parallel sides, we can no longer call it a trapezoid, and we can call it something else, though. We can call it a parallelogram. But this is not a proof, so I don't have to write out a reason why. It would just be the definition of a parallelogram anyways. But there you go. That is what would change about the problem if we move the point E to 7,5. So slope is a very powerful tool. The other very powerful tool is the distance formula. You're going to want to use those whenever you can. You're good at them, and they're easy to work with, so you want to try to use them as often as you can. Let's look at some examples on the backside. So on the backside, what we have is we have a couple of more clear examples, and I'm excited to show you these. So these ones are going to involve some calculations, which is great because I'm sure you feel more comfortable with those calculations than you might have felt with the proof that we just wrote. So let's move on to this guy right here. This is asking you to find a couple of angle measures on an isosceles trapezoid. So our isosceles trapezoid is missing 3 angles, and we need to find N and L and M. Now, please remember that we had the isosceles trapezoid base angles theorem, which stated that a lot of the base angles are going to have the same measure. Like angle K here and angle N, they need to match. Similar to that is L and M need to match as well. I've got all that information written down on my page right here. You don't have to write that down, but I do need you to know that this needs to cross through your brain. Now, let's see if we can take this a little bit further. Right off the bat, the measure of angle N should be super simple because it just needs to match angle K, so that one's going to be 50 degrees. That one's super easy. Excellent. Now, the tougher two are going to be L and M, so let's work on those. Let's reach all the way back to 7,1 and use an old trick that we learned there. What if we took all 4 of these angles and added them together? What would all 4 of them add up to? And that answer would be 360. So that means that if I know that all of them need to add up to 360, I can subtract the 250s that I already know about from the bottom. And when I do that, what's going to end up happening is that's going to give me 260. That 260 right there represents the sum of both L and M. So both of those guys, L and M, are going to add up to 260. Also, L and M need to match, which means they need to be evenly split. So if you take your 260 and you divide it in 2, you will find out that both the L and the M are both going to have the exact same measure, and that measure is 130 degrees. If you look at the picture, the angles look obtuse. And 130 degrees is an obtuse angle, so that works out really, really nicely, and it makes a lot of sense. Let's do another one. Our next one right here is going to be a mid-segment question. So once again, the mid-segment right here is going to be a line formed by 2 midpoints, and we're not given a lot of information, but we need to figure out exactly how long that mid-segment is. The only information we have is this length of this segment at the top, PQ, and this segment at the bottom, SR. The great news here, though, is once again the mid-segment is the average of these. This one's too long and that one's too short. We're looking for a good Goldilocks number in the middle. So that means that if you take the 16 that's too long and add it to the 9 that's too short, and then you cut that value in half or average it, that will give you the value that you want. 16 plus 9 is 25. 25 cut in half is going to give you 2 different answers. One, and the one that I like, is 25 over 2 inches. Or the one that you probably like would be 12.5 inches. Not too short, not too long, right in the middle. Let's do another problem with a kite. So now this one right here says that to prove that the kite has perpendicular diagonals. So what we've got is we've got a couple of diagonals, and we want to try to write a proof. Now remember, whenever it says proof, that really means that that's code for you to do one of two things. Looking at slope is going to be really important, or looking at the distance formula is going to be really important as well. So you're going to want to make sure that you're using one of those two tools. In this case, since we're talking about angle measures, slope is going to be our very best friend. Rather than looking for matching slopes like we had on the front side, we're going to be looking for opposite reciprocal slopes this time. So let's calculate. The two diagonals are AC, and the other one is DB. So I'm going to be calculating two slopes for these guys. AC has got this point 0, 0 and this point 4, 8. So we're going to calculate some slope very quickly and easily. Remember, y is first and then x is second. When we calculate the slope, we're going to get 4 over 8, and that reduces down to 1 over 2. Now when I calculate my second slope, I'm not expecting to get 1 over 2 again, because that would make parallel lines. I'm expecting to get something that is an opposite reciprocal. Let me show you. So dB is going to be 5 minus 1 and 5 minus 7. That is going to give me the value of 4 over negative 2. Now this reduces as well. It's going to reduce down to 2 over 1, and it will be negative. The opposite part here refers to the fact that one of these was positive and the other one is negative. The reciprocal refers to the fact that one is over 2 and this one is 2 over 1. So this is going to show you that AC is perpendicular to DB. Next, I have a you try it problem. Please pause the video now and attempt that you try it problem. I'll put the answer on the screen in a couple seconds. Here's the answer for your you try it problem. Once again, the sum of all of the angles inside any quadrilateral are 360. Then I subtract the two angles that I know, which is the 70 and the 88, which is going to give you 202. Now that 202 represents the sum of angle R and angle T, so it is too big. But luckily for me, I remember that angle R and angle T are congruent to each other, so I'm going to split it, and that gives me the fact that angle T is 101. So is angle R. All right, the last piece that we're going to have right down here is going to be determining whether a statement is always true, sometimes true, or never true. And so we're going to go through our topics here. Diagonals of a trapezoid are congruent. That is only sometimes true. It is true for an isosceles trapezoid, but it is not true for all trapezoids. Opposite sides of a rectangle are congruent. That is always true. So your basic definition for a rectangle is that it will have all perpendicular lines or 90-degree angles, but that doesn't mean that there aren't corollaries to that. So the backup to that is going to be that you will have those congruent sides. Square is a rectangle. That is always true. The definition of a square is that it is both a rhombus and a parallelogram at the same time. It's going to have those pieces that are going to be required in order to make it a rectangle. A square is not a rhombus. That is not true. A rhombus, by definition, has 4 congruent sides, and so does a square. So they are going to be matched together. All angles of a parallelogram are congruent. That is only sometimes true. So some special parallelograms would be rectangles and squares, and so those ones are going to be the case where it's true. But just your regular run-of-the-mill parallelogram, the one that probably lives in your brain like it lives in my brain, those angles are not all congruent. Opposite angles of an isosceles trapezoid are congruent. That is never true. The base angles are congruent, but not opposite angles. Those would be consecutive angles instead. The diagonals of a parallelogram are perpendicular, and that is sometimes true. That is going to be sometimes true for a square. This is similar to what we had talked about with a kite, which is not a parallelogram at all, but that also has perpendicular diagonals. Okay, this has been section 7.5. If you have any questions at all, please get in contact with me by email or join in on the Zoom chat, and we can discuss. Thank you so much.